lesson plan, just quick announcements. Projects are due today at midnight. If you talk to me about an extension, you can also turn it in by Friday at midnight. That's the cutoff though. Evaluations have to be done by Monday at 9 a.m., especially for those of you guys who took the class for credit. It helps to have good turnout on those sorts of things. But first thing I'm going to do is I'm just going to give you a quick recap of all the stuff we did. Just write down the keywords so that you can see where it all fits together. And then anything on the board will be fair game, or anything off the board is fine too. So our first unit, back when we had lots and lots of snow in Boston, we talked about the introductory things were to get us thinking about these issues of computation versus statistics versus models. I made this claim at the very beginning of class that machine learning is famous for a lot of important models. You think about something like graphical models, or someone like Judea Pearl won the Turing Award for using it as a way to reason about uncertainty. It gave lots of improvements over formal deductive logic at the time and gave you very rich probabilistic models. But when you think as an algorithms person, you should also be thinking about those models as coming at a cost. So the richer the model, the more expressive it is for representing things about the way we want to model the world. But the more it comes with computational intractability, especially if you're not careful. Because if you define the problem too broadly, then it's very easy to get stuck with hard problems that are not that relevant for the types of applications you cared about anyways. So one of the classic examples of a really nice, rich interaction between theory and applications is something like the singular value decomposition. So at least my worldview, I think of what the right interaction between algorithms and machine learning is. At the end of the day, if you're an algorithms person, the same way min, cut, max flow, the first time you see it, is this one really great tool that has all of these other implications. Well, as an algorithms person, I kind of want to find what are the right tools and building blocks that can be used in machine learning. So I think of the singular value decomposition as a very classic type of tool because it's certainly a Swiss Army knife, but it's a Swiss Army knife that works in a worst case sense. And then as soon as, one of the main points of this class was that I think when you think about algorithmic building blocks, we've almost run out of tools which work in a worst case sense. And you need to be a lot more careful with designing, what are the right tools. So we talked about the singular value decomposition. We talked about some, applications of it. The natural ones are like taking high-dimensional data, figuring out low-dimensional representations that roughly preserve their structure. Or you can think about it as finding subspaces that preserve as much of the variance as possible, subject to what dimension you want to project them into. And one of the classic applications was to what's called latent semantic indexing. Immediately after we did that, we talked about non-negative matrix factorization. But we talked about some of the sources of hardness for this problem. So it's a great example where non-negative matrix factorization, a lot of the applications, you can think about the features as, in recommendation systems or in topic modeling, as themselves having extra constraints that help it be better posed, but they also come along with hardness results too. That, we saw NP hardness results, we saw even fixed parameter intractability results, but ultimately the path towards giving algorithms was to understand under what conditions we get uniqueness results. So that's where we introduced things like separability, was that the same types of properties that people were looking for that make the problem unique and robust turn out to be pointing the way towards where you should expect for algorithms. And we talked about at the end of Unit 1, we talked about algorithms via that exploit separability. And we talked about some of these applications to topic modeling. And one of my favorite experiments there was that topic modeling has a lot of these really nice toolkits that seem to work well. And we did was we took those toolkits, we fit them to real data, and then we used that as some baseline truth, generated more data, and found that we could actually beat those algorithms in their own game. So there are a lot of settings where when something works in practice, that doesn't mean it's the end of the story. There very likely could be some simpler explanation that can also help you design better algorithms. So we also, had these, this interlude where, one of the main points that I wanted to illustrate with this first unit, well, we also talked about approximation stability in clustering. So clustering is another one of these classic problems which gets solved in practice all the time, but as a worst case view, it's hard. It's even hard to approximate. But there's a notion in which those instances which are hard to approximate are very brittle and fragile things, and they're things where there really isn't a great answer to begin with. So we talked about settings where notions of approximation stability, some notion of why the right answer, the thing that actually optimizes the objective function, if it's really the robust optimum, then that's actually a structural property that you can exploit to get better algorithms that beat the worst case lower bounds. So that was a great way to think about this concept of to what extent does making the problem well posed, robust, or unique point you in the right direction towards finding algorithms and understanding which types of properties you should impose. So our second unit, when the snow continued, so I guess we'll have to figure out where the snow stopped in this course, but it was certainly going on here. I think that might have been the peak, right? So we talked about Spearman's hypothesis. Can anyone remind me what Spearman's hypothesis was? Anyone remember?
Verbal versus math?
Yes. It's that if you're good at math, you should be bad at linguistic things. Or, well, more precisely, what he did was, he had that belief that you could explain test scores using just people's aptitudes in, technical things versus literary things, and that you could explain how these students did on different tests. But, this is one of the earliest applications of factor analysis, but there's a fundamental issue at play here, which was the rotation problem. Which was the issue that in Spearman's setting, we were thinking about given access to a matrix, which we believed there were some factors that validated his hypothesis or maybe didn't. But there's the issue that even if there was a nice factorization, we couldn't necessarily uniquely find it, because any rotation of this nice factorization would produce an equally valid factorization of the data. So that's what led us to things like, tensors, right? So we talked about, basic properties of tensors. We talked about, you remember that we talked about what the linear algebraic toolkit looks like in the tensor world and how pessimistic it is, that all the things that you could compute in the case of matrices, things like rank, low rank approximations, not only are hard, but sometimes they're even less meaningful because, for example, for a tensor, your best rank R explanation could share no factors in common with your best R+1 decomposition. That's something which is completely different. In fact, the most worrisome thing was the notion of border rank, that a tensor could have rank 3, but for any epsilon could have an epsilon good approximation, that's rank 2. So you get into very finicky, brittle algebraic issues. But the one saving grace which made tensors worthwhile was Jenrick's algorithm. That told us conditions in which the factorization really is unique given the matrix and gave us an algorithm that went along with it. And eventually we came back to this issue of giving perturbation bounds for Jenrick's algorithm, which we talked about things like condition number or Gershgorin's theorem to start off with. And when eigen decompositions are well behaved under perturbations, that allowed us to say that even when we're not given the exact access to the tensor, but a very good approximation, which we compute from, for example, empirical moments, then we could still get provably good approximations to the factors. And eventually what we talked about applications to phylogenetic reconstruction. For example, we talked about Steele's distance function. We talked about quartet tests, how to reconstruct the topology of the tree. But then once we had the topology, we went back to Jenrick's algorithm to actually find what the transition matrices are in these phylogenetic trees. We also talked about applications to HMMs. We talked about noisy parity, which is a simple HMM, which the types of observation matrices we see violate those that happen in Generick's algorithm that we need. And that really is a dichotomy between you really do need the factors to be full rank or something close to that to be able to get these algorithms off the ground. We talked about applications to topic modeling, again. And we talked about applications to independent component analysis, where we were assuming that we were given a linear combination of independent random variables, and we want to figure out what's the right basis that makes them independent. So it has this nice cocktail party problem, which I renamed as the NSA problem, because you have n microphones and n people, and you want to be able to figure, n conversations, you want to be able to figure out how to disentangle and deconvolve those distributions. So we also had this interlude at the end of this, which was about semi-random models. So we talked about this 5-Killian SDP for clustering the stochastic block model for covering a Plankton bisection. One of the interesting aspects of this was that many of the algorithms which use statistical properties of some model, they might in principle be over-exploiting them. So they might actually be relying on very rigid criteria. Semi-random models gives us a way to stress test the assumptions we're using. And lo and behold, for things like clustering in the stochastic block model, all but one algorithm ends up failing. And the only thing that I know that works is based on STPs. So that was a kind of strange one. So after that, we talked about sparse recovery. So we talked about the basic sparse recovery problem, where we're trying to find the sparsest solution to a given linear system. We talked about, I gave you this hardness proof, which was based on the weird moment curve. That's actually a trick that comes up a lot. Eventually, again, the same way in Unit 1, we got around the issues that NMF really is hard. Well, the way that we got around these types of issues here was looking for cases where the problem is unique and robust. And in that case, we looked at incoherence. So things like the spikes in Science Dictionary. We ultimately proved uncertainty principles. And we talked about orthogonal matching pursuit as an algorithm that actually recovers almost up to the threshold where we know the uniqueness works. So these types of uncertainty principles were things like a function and its Fourier transform cannot both simultaneously be sparse. And we gave examples of, for example, the Dirac-Cohn function that actually showed that the uncertainty principle was tight beyond that. And that also gave us a different way about thinking about why Grishkorin's theorem is stated the way it is, was because it also told us that there's a certain tightness to the way it's stated. And eventually what we did at the end of this unit was we talked about sparse coding, which is turning the problem on its head where you don't know what is the basis that enables your signal to be sparse, and you're given many different examples, and you want to jointly find a basis that enables a sparse code. We talked about alternating minimization. And we analyzed it through approximate gradient descent. We talked about why it makes progress because it takes steps which are some approximation to an unknown but convex function. And who remembers the name of Pearson's crabs? Anyone remember the species? Nope.
Naples.
Naples, yes. Pearson's Naples crabs. And what he used was the sixth moment test. In fact, if you look in his paper, there's a very prescient comment by George Darwin, asking him how he knows that his method is robust, of course in Old English. And George Darwin has a kind of famous father, but you might not have heard of him. Then we talked about learning via distance-based clustering. So we talked about the Aurora-Canaan algorithm, which is really, an interesting facet of high-dimensional geometry, that Gaussians are like spheres of a particular radius. You can certainly cluster them when the spheres are disjoint, when the radii are just not overlapping. But in fact, even when the radii are quite overlapping, when they actually overlap, the mass in this overlap region is still tiny. And it gave us algorithms whose separation condition was actually n⁴, so much smaller than the radius of this. And ultimately, we actually used PCA to find the span of the means, to actually isolate the subspace in which the separation lives. And that allowed us to get separation conditions which depend on k, the number of components. And ultimately, what we talked about algorithms for learning the parameters, which learn even if you don't have separation. So we talked about learning via the method of moments. And ultimately, we use the heat equation to think about why 6 moments suffice to analyze Pearson's 6th moment test. And ultimately, we gave an interpretation through algebraic geometry. Where to prove things like uniqueness, we're really reasoning about the only solutions to a system of polynomial equations. And then we talked about using quantifier elimination to actually prove that systems of polynomial equations are somewhat stable, as a way to think about why proving uniqueness already gives you a good handle on robust uniqueness too, for these types of problems. And ultimately, one of the sort of punchlines behind learning the parameters, even when you can't do distance-based clustering, is that for mixtures of Gaussians like this, where they come at an axis or something, there's zero separation between them. You can still cluster them well, but that clustering scheme has to depend on what the mixtures are. Because what you'd really want to do is you want to project along a direction of tiny variance for one and pull out all the guys in some narrow interval. So what we could do was, once we learn the parameters without any restrictions, that allows us to use our knowledge of the mixture then to do roughly as well as the Bayes optimal clustering. So it allowed us to do clustering whenever it's possible, not just under separation conditions where you do it based on distances and SVD. All right, and finally, the very last unit that we talked about was we talked about the matrix completion problem. So we talked more particularly about the Netflix problem. And we talked about matrix completion. And there's a whole rich set of problems out there which are really about inverse problems. You're given some structured samples from a structured object. You can think about even sparse recovery as being in this setting where you're given linear combinations. Matrix completion, you're given single observations and you want to be able to reconstruct a structured object, but in a computationally efficient way. So this area goes much deeper. There are all sorts of other problems, like given an entire matrix, which is a low-rank matrix plus a sparse matrix, you're thinking of that as corruptions. You can also separate those two using STP techniques. And there's a huge literature on this. But even in the case of matrix completion, what we talked about the nuclear norm. We talked about its dual characterization. We talked about it as a generalization of the L1 minimization, which works for sparse recovery. And ultimately, we talked about quantum golfing as this technique in the dual for showing that the particular plankton solution you want is the optimal solution to your STP. It's very similar to what happened for semi-random models where we passed to the dual, and we used random matrix theory to prove that our guess showed only the plankton thing is the right answer for the STP. And finally, the very last topic we talked about was we talked about alternating minimization, again, based on principal angles. And that led us to today. So this is all that we covered. I'm going to open it up to you guys. So now you guys get to quiz me or ask me whatever's on your mind. Yes?
You mentioned that you didn't have time to go over how tensor methods are used in neuroscience. I was curious briefly what they're used for, like basically what they solve.
Sorry, could you repeat that?
So you mentioned tensor methods are popular in neuroscience right now.
I think I said that they were popular in psychometrics.
Oh, okay.
Yeah. So psychometrics. So the funny thing is that this algorithm, the first time I taught this course, I attributed it to different people, and I think this is the original source, but it's been rediscovered at least 4 or 5 times. And part of the reason that it keeps getting rediscovered is because the original discovery, well, first of all, was in, Generic didn't write this paper, someone else did, and they credited him but gave the algorithm. But one of the big issues was that they only used it for talking about uniqueness. So they only cared about why, when, what conditions you can place on the factors, where its low rank decomposition is unique. And there are actually better uniqueness conditions than Generic's thing, because Generic's thing only works for a number of factors, R, which is at most n, because you need the factors themselves to be linearly dependent. Whereas there are stronger conditions like Kruskal's uniqueness condition, which end up working for third order tensors up to 3/2 times n. So in fact, what happened is that these results happened in somewhat close progression, and then in the psychometrics community, all of them cited Kruskal's uniqueness condition, and not Generic's because they thought of it as strictly stronger. But the issue is that there's no algorithm to go with it. So that's actually what makes it stronger, is the algorithmic aspects of the uniqueness. So psychometrics actually, for some reason, I don't actually know too much about that community, but I think you could also make the claim that they played a big role in inventing NMF. That's another problem which has been phrased a few times at least. But it was called like self-modeling curve resolution or something. So I don't actually know what's going on in that community, but they have very good definitions and problems. So.
Something that is quite common to all these kind of estimation problems that we covered is that we didn't really analyze it through the lens of approximation algorithms, where the objective of fitting the model or explaining the model is only achieved at like some constant approximation or whatever approximate. So is it like not common to study these kind of problems?
Okay, so I guess when you talk about approximation, there are a few ways that you could think about how people study approximation problems and how they relate to this. So one issue is that a lot of times, if you take something like matrix completion, there's actually a tensor version of this problem too. So matrix, the nuclear norm that we define, if you look at the set of nuclear norm at most 1 solutions, if you look at the X, where nuclear norm of X is at most 1, then that's actually the same object as convex hull of AB transpose, where A and B have norm at most 1. So a lot of times for these types of linear inverse problems, there's some norm that's guiding you, but you can really define it based on what that is as a convex body that you're using to try and figure out what's the smallest scaling of that convex body that contains the hypothesis that's consistent with my data. So there are a lot of settings beyond what we talked about here where there are hard norms, which if you could compute would be awesome at solving inverse problems. So for tensors, for the tensor version, one thing you could try is you could look at a body which is the convex hull of these rank 1 and normalized terms. But the problem is that objects like this are actually hard to approximate, or hard to compute exactly. They're hard to approximate. But what plays a big role in, if you could optimize over this, you would get very strong information theoretic bounds for reconstructing tensors. What plays a big role is finding a geometric approximation to it, which has roughly the same volume, because that's the sense in which it governs how many observations you need to pin down which hypothesis is the right one. That's one notion where approximation comes up, is when you're talking about solving linear inverse problems through convex programs, you're really talking about creating a relaxation of some object that you'd like to optimize over. But the notions of what it means to be a good approximation are very different in the applications to learning than in worst case approximation algorithms, because I don't so much care if there's a direction where my two relaxations produce very different answers, but I care about in a typical direction that they produce the right thing. So it's more of an average case notion of hardness. There was another question that was mixed in there, which I wasn't sure which one you're asking. But another problem that really comes up is, what happens if you have deviations in your model and you just know that the samples you're getting are close to the true model? So for example, you want to learn the parameters of a mixture of Gaussians, but you're only assuming you're given samples from something that has total variation distance a tenth to a mixture of Gaussians. Can you find something that's actually that close?
Actually, my question maybe was not on the modeling aspect, but more on the optimization itself. So all these problems define some kind of objective. And my question is, instead of having exact reconstruction, or can we be interested in a solution that is producing an objective that is, for instance, half of the optimal objective, or something like that? That still satisfies whatever constraints we put in the model. That makes it a feasible solution, but the objective, I don't know if it makes sense for all the different.
Not for all of them, but for something, again, like matrix completion.
Yes.
Instead of looking at, this was the caveat that I added in the beginning, that when you actually care about these problems, no matrix is low rank. So what you actually need is you need something that still has interesting guarantees when you're close to low rank. Now there are many such guarantees. There's some of them, there's like a Candace and Plan paper, which has the nice property that it works with noisy matrix completion and shows you that you get a good approximation to the true matrix. After all, you can't recover the true matrix there. But one of the nice things is that in the case where you turn the noise to 0, it recovers the exact completion results. That said, it doesn't tolerate noise as well as some of the other things. And some of the other ones take more of a statistical learning theory approach, where you just want to find, some hypothesis that fits the data almost as well as, what the best thing would. And there are similar guarantees there too.
And this is exact reconstruction.
No, approximate. So even in the noisy case, you can ask, can I compete with the best low rank matrix that approximates it? And there are settings where you can. That's of course the setting where you care most about is what happens in the presence of noise. So that's certainly an important caveat. Is there another question? Yep.
Yeah, well, okay, so this isn't asking anything, I can ask less math, well, not math question, but advice question on these sorts of proofs.
Yeah.
So short proofs I've historically been okay with as far as trying to prove something. But reading a lot of these papers, these proofs can go on for 3 pages, and I'm wondering,
Can go on for a lot longer than that.
Okay, I've seen ones that go on for 20 pages, but and I'm sure there are ones that go on for longer than that. What is the intuition that people use to figure out how to start or even continue these long proofs and figure out even where they're going when they don't know what the target is necessarily?
That's a great question, and I can only answer for myself there, right? Because people have very different strategies for these things. But for me, sometimes I think it happens that you end up writing a really long paper. So for example, the 2 papers we talked about in mixtures of Gaussians that I've written are a combined 100-something pages, right? But then you'll come to the point where even you don't remember some of the details, even if you wrote some of those parts in the proof, right? Because there's a difference between which pieces in the proof should surprise you and which pieces shouldn't. So I think that, that's at least certainly one of my strategies in doing this, is that you start off with the problem that you would, care about, but you keep trying to isolate what you think is an even easier version of it that's more concrete to wrap your, head around, but you still think solving it would give you some insights about the original one. So you sort of slowly work up to that. And one of the challenges is that then when you write the paper, a lot of times the footprints to how you actually came up with that are not always present, because sometimes that trajectory is sort of meandered and taken its own path. So, even when you're reading a paper, which, someone else wrote and is very long, I think it's very instructive to sit down and think about what is the simplest special case that illustrates these ideas. Because after all, that's how you'd present it in the class, that's how you'd explain it to someone else, and that's how you try and derive insights based on the paper when you think it's relevant to something you want to do, is at a high-level view of the problem, which ignores a lot of the details, but you think is roughly a good hypothesis for how their approach is working. So the details can be very messy, but also having an abstraction of it that you can explain to other people quickly, I think, is very important, both for understanding it well yourself and deeply, but also in being able to try and apply those techniques to other things.
So neural networks have come back a lot in the last 8-10
Yeah, I noticed.
Yeah, in practice, but it doesn't seem like anyone's really resolved a lot of the local minimum problems, or at least as far as I can tell, applied some of the tools we've talked about to figure out why they seem to work somewhat in practice. Have you?
Oren, you have anything to add?
Oh, okay.
Well, I completely agree with that. Like, most of the research is completely empirical, right?
Yeah.
Yeah. Is there anything at all that you've seen that tries to apply anything that we've seen in class to?
I've seen, this is certainly a huge topic, right? Because, one of the issues that there's, you hear deep learning all the time, right?
Yeah.
And for me, the truths are, A, empirically it's amazing. So they've obviously done something really cool. But B, you look at their explanations, and these are explanations which you could create another thing that doesn't work that fits all of those explanations, right? So, there's this gap between the empirical things that they produce, which are amazing, and the sales pitch of, you have the visual cortex and then you do something, right? But you have to be really careful because, if you look back 30 years, right? So there was this really cool experiment where people, got interested in neural nets back then. They proved all sorts of wonderful information theoretic properties. Things like if you have a 2-layer net, then any continuous function class, you can arbitrarily well approximate it by some neural network. This is really just a statement in real analysis based on the Stone-Weierstrass theorem about if you have a rich enough family, being able to approximate anything continuous. But the issue is, how large does that need to be? How well can you fit? And people had these empirical things where they tried them out on 2 different composers. They presented them with the sheet music. They trained this neural network to be able to tell apart the 2 different pieces of sheet music, right? It was amazing, like, is it Bach or Chopin? And then it turned out to not be so amazing. So Minsky figured out what these neural nets were actually doing, was they're just looking at the color of the paper because of how old the composers were. So you have to be very careful when you have, black box function, which can fit any function. It can work for sort of mysterious reasons. I actually, spent some time on Wall Street when I was an undergrad, working on automated derivative trading networks. And they have a lot of neural nets that they use, for trying to figure out what are good, trading strategies, these sorts of things. Now, one of the big issues is that if you take a neural net which you don't understand what's making it work, you just know that it seems to be producing good things. You have, X different banks which are allegedly independent, and they're all fitting to the same set of data, which goes back until the previous crash, because if you fit to the crash, you would look back in what your expected returns are, and no one would let you do that strategy. So you're fitting to the same 7-year window, but you're all training on the same data, and these neural nets could be learning the same things. So you've in essence, created a lot of correlation, which is impossible to understand in the different trading strategies because you're fitting networks that you don't know why they work to the same set of data and potentially overfitting them. That's kind of an issue. I mean, I think a huge question for deep learning is any sort of even embarrassingly simple problem that you could prove theoretically that it's doing something interesting would be quite something. Because one of the biggest issues that we understand for a single layer, what's going on is you're essentially doing some form of PCA or some other function like this. But now as soon as you take 2 layers and you start talking about back propagation, where you're tuning the weights in one layer and the weights in the other, that has a very complex interaction. Because how you tune the weights at the top layer can then be influenced by how you tune the weights of the other layer, and one of them is not static while the other is moving. The important thing is they're both moving together. So it's a very complicated dynamics, and understanding there's a lot of intuition for maybe why this should work and be a smart idea. But proving that it does something fundamentally different than what's in our normal algorithmic toolkit, even in a very embarrassing model, I think would go away a huge step towards trying to understand why it works. So deep learning is probably one of the things that keeps me up at night, but I think, to be honest, you have to sort of choose your battles a little wisely with, if you took a net that people use on ImageNet and tried to explain that one, that'd probably be really tough. One of the things that got me interested in sparse coding is that in order to have an interesting way to stack different pieces you can solve inverse problems for, you need that the inverse problem is nonlinear. Because you need that given your set of observations, the map to the representation is itself a nonlinear map, which is something you could compute via orthogonal matching pursuit or L1 minimization. It's trying to find a sparse thing, so of course it's going to be a nonlinear map. And then at least when you compose them, you're getting a lot of stacked nonlinear behavior. So even understanding it in the first layer and understanding what alternating minimization does is not so straightforward. But if you were to do things like undercomplete dictionaries, your inverse problem, where it has full column rank, your inverse is actually a linear function. That would be bad because stacking them would just be one collectively linear function that you could flag. So even there, I think the question is, what are the right building blocks? Because people build up deep nets in very different ways and they engineer them with different things. But the question is, from nonlinear building blocks that you understand, what sorts of richer functionality can you build up? And I don't even know what happens when you add 2 of them together.
So what are potential good open questions that are very simple about neural nets that one could tackle?
They're not simple. They're simple.
Well, simple compared to
they're
other
state. They're very hard. So, one of my favorite ones is, if you take a polynomial, which x is itself a vector, and you're thinking about this polynomial as having, n variables because, x is length n, you think of it as having d degree. But the important thing is you're thinking of it as being s sparse, meaning that there are only s monomials that show up in this representation. It turns out that if you choose x to be, Gaussian, and you give me x and p of x, and you do this many times, that there actually is a polytime algorithm. And by here I mean polynomial in n 4 to the d, so it's a bad dependence on d, and poly in s time algorithm to recover p. But the important thing about this is even though it's exponentially bad in the degree, it's not n to the d. So there's actually a trivial n to the d algorithm for this, which would be I take my n variable degree d polynomial, and I treat each of the monomials as an independent variable. And I would just be solving a linear regression problem on n to the d variables. And I wouldn't take advantage of the sparsity or the fact that the terms have a relationship to each other. So this is a kind of surprising thing. It's just a purely algorithmic statement. Truth be told, it's quite brittle to the Gaussian assumptions. But one of the things is that if you took there are proofs that 2-layered nets can also solve this problem, where you're thinking about some n variables here, and actually I've sort of drawn this the wrong way because this middle layer is really, really wide. And what happens is you randomly initialize these inner weights, and you have some sort of threshold here, and you randomly initialize these weights, and you have some threshold. And there are proofs that this can actually solve this problem. But the trouble is that the number of hidden nodes you need here is like n to the 8d. So this is bad because what it's actually exploiting is the fact that when you randomly initialize, you're hoping that every possible monomial in your essentially linear regression problem will show up someplace here. That each one of these guys will sort of represent one monomial over the others. And the top layer is assigned to just picking out which of those monomials should actually show up in your linear regression problem. So it's a setting where you're not actually taking advantage of things like the sparsity. Now, if you think about, this would be a very static view of what backprop would do. You would randomly initialize these things, and you would sort of keep the weights fixed, but you would do backprop on this top layer for selecting out which terms to be in your linear regression. But what people believe is that you should be able to get away with a much smaller number of hidden nodes, something that's polynomial in n, maybe in 4 to the d in s. But the issue then is that you can't hope each monomial in your regression shows up disjointly. But maybe backprop by simultaneously changing these weights and these weights, it can find one of the terms, make progress on that term, and then recurse and find new terms. So in the same way, interactively, updating both of these weights allows you to explore in a sort of non-static way where I'm not just hoping all the pieces are out there and I just have to assemble. So it's a very rich family of things that you can represent with even pretty tight intermediate layers. But the question is, how could you possibly fit into that model well with something as simple as backprop, which is very easy to describe, but seems very difficult to actually analyze. So I think this is a great challenge problem. It's simple to state, and it's very, very hard.
Very different topic. Back to matrix completion. One kind of variant that you write, I think, is when you have corrupted, you have to observe corrupted data, where the corruption is not just some small noise, but possibly a large noise, but it just has some scarcity structure. So the noise is itself sparse, but it could be very large. So what other, and for this case, I think we can have some like there exists some provable reconstruction.
Yeah. So, I mean, a lot of papers on matrix completion. They all have, fairly incomparable guarantees, unless they haven't understood the previous papers. But, one of the stronger types of guarantees, which I think captures many of the ways you would want to extend it, but is not, the full thrust of what all you can do, is if you look at something like, the error of your hypothesis to the true matrix, which, you find this in polytime, and you measure it as the average error. So one thing that you can do is you can show that with high probability, this will be at most some epsilon plus eta, where eta is the error of the best low rank approximation. So even then, it actually doesn't matter as long as you're assuming that the samples come from something which is close to a low rank matrix. But here your notion of closeness is an average notion of closeness on the entries. Then you can actually fit almost as well as the true thing in polytime. Now it gets a little finicky talking about what this epsilon is and how it affects the sample complexity. The other thing is that you're not taking advantage of things like prior knowledge about where that errors are scattered. If you know for a fact they're sparse and they're sparsely corrupted, then there are a lot of other tricks you can do with fancier STPs that I could imagine working by explicitly encoding some relaxation of your knowledge on how the observations are scattered, how the errors are scattered. But it's probably 4,000 papers on matrix completion, so it's that's a good starting point. There's this paper of Cerebro and Schreidman, which is really nice, which gets guarantees of this form. It at least is in the right ballpark, that it works nearly as well as finding the best low rank approximation, and it's efficient. But then there are a lot of extensions you can do after that, and it's not, I don't know that much about which of the things are known and unknown there.
So in a different direction, completely, there's a lot of interesting models and algorithms in probabilistic graphical models. So for example, there's like loopPVP.
Yes.
Can you talk about it a little bit?
Yes. You know, the unit which I would have loved to cover if there was more stuff there would be graphical models. But graphical models, I think, are one of the other, really important sets of problems. The same way, deep nets have been so influential. I mean, this is something that I talked about at the very beginning, that, Judea Pearl won the Turing Award for graphical models. Because it also makes sense to think about what was true, before his work, was that people were doing, especially here at MIT, back at the time, they were doing deductive forms of logic. So how they were trying to solve like the Turing test was have a axiomatic list of rules for how you should reply in different situations, right? And they were trying to build in axioms and then talk about an AI as deducing new axioms. But there are a lot of phenomena which it doesn't represent. So one of the most important ones is some notion of explaining away. So if you think about like a patient with some symptoms and some diseases, that might give you a prior on which of the diseases it might be. Because maybe there's two diseases that could have led to this symptom. But then when you observe a new symptom that could only have come from one of those two diseases, you'll immediately change your posterior and you'll be concentrated on that one disease. So even though before you observed that symptom, you thought it was maybe equally likely to be one of these two diseases, you have an explaining away phenomenon that now you understand where your observations came from. And you also have things like when you observe some things, variables which were not independent can become independent. So, Judea Pearl also, in addition to formalizing, graphical models, gave a lot of complicated rules for what are the axioms of independence that a graphical model abides by. And there's a lot of then questions about, if it's a really nice way to model interesting distributions, which it for sure is, algorithmically, can you take advantage of that? So one of the most basic things is that it allows you to encode a distribution, on n things, with using way fewer than 2 to the n values. So you're using a tiny, tiny set of parameters because you're encoding implicitly what the distribution is, but you're also encoding what you think of as the important structural aspects, which pieces are independent and how from each other. But if an algorithm needs 2 to the n time to actually fit the parameters of that model, then all those structural properties and conciseness of representations end up not being so meaningful. So one of the, what do we know in graphical models are truthful things. It depends on which types of problems you study. You can ask the question of, can I learn what the underlying topology is of the graph structure? Can I fit its parameters? Can I sample from it? Can I compute its posterior? They all have very different theories. Probably computing the posterior is one of the hardest problems there, so it requires the most assumptions. But one of the big issues when you look at something like, can I compute the posterior and use my graphical model to make deductions? One thing you can certainly handle is something which has a tree-like structure. So if it has sort of directed influences and it's organized like a tree, then pieces have very simple conditional independences. Because once you know the parent, everything on top is independent from the things on the bottom, and allows you to do dynamic programming to actually compute, what these things are, what the posterior should be. Those things can be extended to things which are found in tree width as well. But one of the biggest issues is that what makes a graphical model easy to work with should not be its topology. As in, if I took a real world graphical model, not only would its topology not be simple and it wouldn't have bounded tree width, but the thought experiment is that if I took a real world graphical model, I believed if I cared enough, I could fit its parameters in a way that makes the inverse problem extremely brittle and computationally hard. What should make it easy is actually what the settings of the parameters are, that they should lead you to the same, they should all, give you many sorts of independent, evidence that point you in the same direction. So if you think about like a disease network with diseases and symptoms, what should make it easy to do inference there is the fact that many different symptoms can help lead you to the same type of conclusion. So the fact that there really is a robust answer you're looking for really prunes down the types of problems you would care about in a way that's orthogonal to pruning down the problem by only looking at its topology. So that to me is one of the biggest issues is, how does the aspect that I only care about certain types of, inverse problems in graphical models in practice, where the answer is robust, how does that play in with what are the structural assumptions I need to actually get my algorithms off the ground? And I think that's a very challenging question.
In real world, the topology would like be concentrated on something that has simple, like the graph would be concentrated on the graph that has a simple topology.
No, it depends on how you define topology. If you define topology based on tree width,
yeah,
absolutely not. So if you take the disease network, right, with just symptoms and diseases, which diseases influence which symptoms, there for sure will be a large clique minor. It's even a pretty dense bipartite graph. It's non-trivially dense.
So like to answer, like, I guess depends on the applications. Like for instance, I know choice modeling. Sometimes like this is not an realistic assumption, and I guess you could do some pruning by doing some feed fights by selecting what adds information to the model.
Yeah, I mean, I think it depends. Obviously, there are places where you can assume that it's bounded tree width, but I think the places where you can't is a much larger set. And in fact, the issue is that the particular disease network I'm talking about is this QMR DET thing, which took hundreds of thousands of man hours to create, because what they did was they asked doctors various questions. If you were in this scenario, what would you do? And they used it to actually hand design the parameters of this network. So it's not like you can really cut up this graph into smaller pieces without precluding some of the scenarios that actually do come up in some of those scenarios. It could be that conditioned on your evidence, your symptoms, you can remove some aspects, but it should not be independent of the evidence. So that's one of the big differences, that people also study graphical models in statistical physics, but there they talk about what's the lowest temperature at which these Ising models mix. And it's really about at that temperature you can cut up the graph into constant size pieces so that one particle doesn't depend on anything in a strong way that's going on outside of it. But I think the reasons that make models easy in statistical physics has to do with these correlation decay aspects, that particles don't depend on too long-range phenomenon. But that's a very different type of thing that I can see being the phenomenon at play for something like a disease network. Because I think if you took that graphical model that they've hand-constructed and cut it up, you would end up with something much worse in terms of its predictive power. Of course, we don't really know for sure, but that's my opinion on it.
Because the underlying direction is that combinatorial approaches can found will fail because they will only rely on topology.
Exactly. But the other way to put it, right, is that's why I designed that thought experiment, was because any combinatorial approach, if it can only work for all settings of the parameters, conditioned on the topology, then if I took a real-world disease network, I'm sure I could come up with a setting of the parameters where you really couldn't solve these problems. So then those combinatorial things can't be the ones that are explaining why things work so well on those particular models.
So what are some other interesting or challenging open algorithmic questions in the area?
All right, so I don't know where to begin on this. Prove alternating minimization works. That'd be quite interesting. Understand what conditions of NNF make it easy in other applications. So it makes it easy in applications of topic modeling, the notion of separability, as something which you can have empirical evidence that it satisfies. But part of the reason NNF is so popular is because it really represents, single hidden variable, two sets of observations, types of models. So it represents a lot of types of things like, collaborative filtering, Netflix prize problems, all sorts of things, even image segmentation. But what makes the problem empirically easy there, via heuristics that we don't know how to analyze, should be a very different type of structural result. Here, one of my favorite open questions is, can you get an algorithmic version of Kruskal's uniqueness theorem? Can you get an algorithm which works for over-complete tensor decomposition that doesn't require, strong conditions on the factors like near orthogonality or something? Because in most of the applications we talked about, you really don't have that kind of control on it. One of the other things is that, even then, what you're really hoping was that your statistics have this low rank decomposition. So the abstraction for what's going on here is you have your tensor decomposition algorithm, and you think about what statistics you can compute and gather from your model, which will have a low rank tensor structure, because then you can solve an inverse problem and find something about the features. But there's a lot more art to actually being able to manufacture a tensor which has a low rank structure. So in ICA, when we did the natural approach, it didn't quite have a low rank structure, but we were able to subtract off other tensors from it to create that. So the issue is that those formulas end up being kind of magical things in their own right, because they're cumulants in the case of ICA. And it'd be great to have a more algorithmic understanding of when you can and can't massage statistics from a problem into a low-rank tensor, because there are a lot more creative ways you can do it than just measuring third-order statistics, because you can do things that get you out of that even when that doesn't work. So that's certainly one setting. One of the issues really, though, is that some of the tensor methods can be very dependent on the distributional assumptions. So as soon as you deviate from some of those independence things, then things go haywire. There are applications of tensor methods to community detection, and the only thing that I know that works for community detection in the semi-random model is the SDP. There are all sorts of questions about, I would love to see, for example, for alternating minimization, can you analyze in a two-layer thing which has sparse coding in each of the layers? That would be amazing because of the potential implications for deep learning. And for matrix completion, I think some of my favorite open problems, the things that I would have wanted to get to if we had more time, was that there's this rich understanding of using semi-definite programs to solve inverse problems when you have a structured object. And most of the settings where people can do that are settings where you happen to get as well as you could information theoretically. You remember for matrix completion, we needed n times r times polylog n observations, and the model itself has n times r parameters. But for tensors, there's actually a gap between the computational and statistical things that you can do. So it turns out there that you can explore it through like hierarchies of SDPs, and you can start to understand what are the trade-offs between sample complexity and computational complexity. For me, that's one of the main driving forces going forward in the interaction with statistics, is that usually the way statistics is set up, you don't think about computational constraints. Now, when you impose computational constraints, there are a lot of issues. There are some settings where imposing that doesn't change the fact that you can recover something close to the statistical minimum, like for matrix completion. There are other cases like something called sparse PCA, where once you add computational constraints, you get stuck with a dumb algorithm that does something naive like that. But what I think is really interesting is, those are great first steps, but what do the trade-offs between computation and statistics look like? Are there interesting new algorithms to discover that have different sorts of behavior along the way? And one of the big issues is, conceptually and philosophically, is that we only care about average case problems here. So when you care about one average case problem and you've studied it for a while and you have a good sense that maybe it's a reasonable starting point for an assumption of hardness, when you see a new average case problem, you're very unlikely to be able to find a reduction between the two that preserves the naturalness of the distribution. So this is something that cryptography has really encountered, is that they care about basing public key encryption on worst case hardness, because they care about average case problems for generating your keys. They've shown that you can't do that without the polynomial hierarchy collapsing. But their notion of average cases, there exists a sampleable distribution, which you can use to generate hard instances and keys. But when you talk about learning, if you only care about nice distributions, then you have a scientific issue of how do you actually explore the space of what you can and can't do in polytime, without making one assumption per problem, and in a world where you can't really rely on reductions to prove everything you want to prove. So that's at least one of the big philosophical questions there, is we really don't have enough average case assumptions to build up a theory of, computational versus statistical trade-offs yet. We could try exploring them through hierarchies and try experimenting with new average case problems, and those are all, I think, great things to do. But, due to snow, we ran out of time on that, and maybe it's good. That wouldn't have been super easy, but it would have been fun for me and painful for you. So.
Ankur, what about the relation of all these topics with statistical learning theory and pack learning and things like that?
So this actually type of view is much more statistical learning theory. As you can think about it as you solve your STP and you find a low nuclear norm solution. Why? Because the matrix itself would have low nuclear norm, and you're looking for the smallest nuclear norm thing that agrees with your observations. You can think about your observation as being empirical error, because that's on your training set how well you're doing. And what you want to show is that the true error going forward is not too much larger. So this would be the best empirical error you hope for. You always find something like that because M itself would be good, or its low rank approximation. And then, so it's really a question about that family of hypotheses. How not rich is it, so that when you fit to your data and you have low empirical error, does that imply you have low true error too? So that's where you get into a lot of empirical process theory, is why can't this family of hypotheses fit random functions? That's the same type of thing that goes in the pack learning bounds for proving generalization bounds, but it's also the same type of thing that gives you matrix completion guarantees that look like this, that also work in the noisy setting too. But that's a great question. Part of the reason that the empirical process theory is a really interesting tool, part of the reason I didn't talk about pack learning is pack learning has a very different kind of behavior. So there, what you're doing is you assume there's some family of hypotheses, and you're given samples and observations, according to what that unknown hypothesis labels them as. So one of the classic things is that I can pack learn a half space. Because what I would do is I would take many samples, I'd see my labels, and I'd find any half space that's consistent with the labels I've seen so far. And that, lo and behold, will have low true error going forward. That's not hard to show. But one of the issues is once you have two half spaces, the intersection of two half spaces, the best algorithms we know run in exponential time. And part of the issue is that pack learning is something which, when you take more and more samples in some of those models, it doesn't seem like the computational issues go away. So taking more samples doesn't help you, because the hard part of the problem is finding any low description complexity hypothesis that agrees with your data so far. And when I take more and more samples, that continues to be a computationally hard problem, as far as we know. Whereas in a lot of these settings, for something like mixtures of Gaussians, it's known, for example, that it's NP hard to compute the maximum likelihood estimator. But how do you reconcile that with the fact that you really can compute its parameters if you're given enough samples to the model? Is that as you take more and more samples, the problem itself of finding the maximum likelihood becomes better and better posed. So that nonlinear function sort of smooths itself out. And even when people prove hardness results for some of these problems that you can't compute the maximum likelihood estimator, it's not really a barrier, because it just means that you can't compute the information theoretically optimal estimate. That doesn't mean there's not another estimator that converges at a still pretty good rate that you can solve in polynomial time. So these are problems which one should not be scared of the hardness results for a lot of them, because there always seems to be a way around them. Whereas in packed learning, especially for learning an intersection of two half spaces, I think one should probably be a bit more timid about what you believe algorithmically is true there. People even base crypto systems on these things.
So could you talk a little bit more about how come the sample complexity affects one area and the other one it doesn't? I'm not quite sure if I understood fully.
Yeah. So let's do a thought experiment, right? So maximum likelihood is, in some sense, the information theoretically optimal thing to do. There are a lot of caveats to that statement, and it's misused a lot, but let's take it at face value for now, right? You take any of these problems, you take topic modeling, you have a stochastic model, you observe some things. You take mixtures of Gaussians, you have a stochastic model, you observe some things. Figuring out what is the best possible deduction you can make from your observations. If you think about one of your samples, like one document, What it teaches you about what the topics are is not an isolated thing, but it depends on what all the other documents have taught you along the way. And it's a very intricate optimization problem, right? So it becomes an insanely hard to wrap your head around optimization problem. But if you just care about, do I have an estimator which is converging to the right thing, maybe 1/10 of the documents are ones which you can actually make good deductions based on. So you take a factor 10 more samples, you throw away the things that are hard to get as much juice as possible out of, but the things that are easy, you use them to feed your estimator and converge to the right answer. That's exactly what happens with separability, is if you knew those anchor words, you could ignore the non-anchor words, documents that contain none of them, but you could still make progress on the ones that do contain them and figure out how you should update your parameters. So you're sort of sidestepping the issue that figuring out everything you should have learned from your observations is an incredibly interdependent problem, but you're making it easier by hoping that there's a trapdoor that's still pointing you towards the right answer. And that's always something that you can do for these problems. Whereas in packed learning, it's a lot harder to do that, to get these things to work out. So in some of the statistical learning theory things, I'm not as convinced that there's a nuanced theory about how taking more samples can alleviate computational intractability issues in much the same way. Only have a few minutes, so any even off-the-wall questions?
So I have another question.
Anyone besides Brando first? Brando can bat cleanup.
I'd be interested in hearing just a couple sentences of what you're working on, right now, just in general, what your interests are at the moment.
Yeah, so this class is kind of like what my worldview is anyway. So, I mean, what I'm working on is I had something on tensor completion, which I would have loved to talk about, but I think it's a bit technical. So that's really getting to the heart of, for these linear inverse problems, where are there phase transitions in computational versus statistical trade-offs? One of the other things that I care about these days is, in a lot of other statistical things, this is something that I could not talk about here, but Lotzi's project was on this, was, there are a lot of settings where there are natural plug-in estimators for computing some quantities. You want to compute the entropy of some distribution. Well, if you had perfect, probabilities for, values for the probability different things occurred, then there's some true, natural unbiased function that takes you to the parameter you want to estimate. But there are a lot of settings where you can actually create bias versus variance trade-offs in very non-trivial ways to actually create better than plug-in estimators and, do things like approximate inclusion-exclusion and have more robust formulas that compute the same types of quantities. So that's something which, I think is really mathematically interesting. As a conceptual thing, taking a step back, one of the things which certainly made a big influence on me was we have this algorithm for learning mixtures of Gaussians. And what I claim is that there's actually a statistical corollary of that algorithm that I don't know any other way to prove. So by virtue of learning the parameters of the mixture within an epsilon, it means, algorithmically with polynumber of samples, it means that there cannot be any two mixtures whose parameters are epsilon different that produce almost the same distribution, because otherwise the algorithm would have had to fail. Okay? So the same way that actually, I think we take for granted that in a lot of settings we have all of the statistical bounds we could ever want. Actually, I don't think that's really true, that some of the questions which I care a lot about are settings where having the algorithms I would want to have would yield statistical corollaries that we don't have in their own right. And I think that has to do with the way statistics has set up its definitions. So they all go back to like Fisher and maximum likelihood, and there's a notion called like asymptotic efficiency, namely that you converge as fast as possible with the right answer eventually. So those are all asymptotic definitions because you treat the problem size as fixed, you sum the number of samples to infinity, so that you can take a Taylor expansion of the log likelihood. And it's the curvature around the true point you're looking for that governs eventually how fast you can converge. But when you analyze things like the curvature, you're not saying anything about finite sample complexity bounds and what the radius of convergence is there. Whereas any algorithm would have to be telling you something that gives you an effective bound. So actually, you know, one of the pie in the sky things that I'm actually interested in these days is, I guess I've been dabbling a bit in analytic number theory, because what they do there is you want to prove properties about the primes. So you want to prove that, you know, they have these pseudo-random properties. What you really do is, you know, most of the theories there, the hypotheses or open questions are about, do the primes behave as if they're a random set of that density? And you're just trying to prove that they have those pseudo-random properties. And they have all of these amazing test functions, which if you look random according to those test functions, there's a sense in which you're pseudo-random. So those test functions, they really give you very good effective bounds, because people in analytic number theory care about, you know, how many primes out do I need to go to get this kind of behavior. So those types of test functions, the same way that the method of moments is really using low degree polynomials as a test function, I think there's no reason that our test functions always have to be things that you could guess, like low degree polynomials. And it would be much more interesting if, you know, understanding machine learning algorithmically is prescriptive and not just descriptive. So instead of just explaining Pearson's 6-moment test, and anyone could have guessed, you know, use method of moments and use low degree polynomials, well, what if creating richer families of test functions leads you to different algorithms that do better? That's part of the reason I care about non-plug-in estimators, is because when you have these perfect estimators, there can be really non-trivial ways to improve them in the finite sample regime, which draw on a lot of tools from math. So the same way that I think that some of the weaknesses and some of the statistical definitions that originate with Fisher are things which, you know, algorithms have to circumvent and have a lot closer connection to math in general. But that's more of a pie in the sky one. Maybe you put me in a math department and I talk to number theorists. I don't know. Those things happen. All right, Brando, you're up.
Awesome.
Uh-oh.
So, do you have anything to say about manifold learning?
Yeah, you're not gonna like it.
No? Okay. Why not?
So let me tell you what I don't like about manifold learning, and I would love to be proven wrong. So manifold learning, a lot of times what you think of is, you know, so think about SVD. You're just assuming that there's a low dimension subspace that contains most of your interesting information. And you can efficiently find it. That's awesome, right? And you need few samples to do so. Now, what if your points live on some manifold? So what if they're in n dimensions and it's an r-dimensional manifold? So there are provable guarantees for manifold learning. But what they all degenerate to doing is, if you have an arbitrary manifold and you don't have any constraints on, you know, what it looks like and how it looks at a global scale, you only have some local curvature types of things, then what you're really stuck doing is, for each sample point, you're hoping there are enough nearby points that you can connect to them and figure out the curvature locally. So you can only learn something about a point based on what purely very close by things teach you. And the resulting algorithms always have some sample complexity bound, which is NV, in order to handle some of these curvature issues. So they need to take so many samples, you know, roughly n to the r is what you need for some of these manifold things, so that you do have even some close by points that you can connect to and be guaranteed that they're sort of, you know, on a geodesic from one to the other. But that itself is a huge barrier, because, you know, there's a sense in which, you know, deep learning, if you look at Boltzmann machines, it's some manifold and some regularization. But one of the big differences is that you learn from all of your sample points, not just the local ones. So to me, the sort of fact that there isn't enough constraints, it's very natural to think about these things living on a manifold. But if you don't assume anything but something tame like the curvature, then you really are stuck only locally learning. And that seems to miss what makes, you know, some of the other things work. So manifold learning, from my perspective, can work for fairly small R, but then as soon as you blow up to, you know, larger R, which is what you need, for example, for like ImageNet and other sorts of applications, then I think there are issues with how the problem is posed right now, where I wouldn't see how to improve on it without changing the problem, and I don't know what's the right way to change the problem to get around that issue. That's just my perspective. And obviously it didn't make it into one of these units, so I'm a little biased, but all right, that's it, let's call it. So thanks for coming. 9:30, you guys woke up how many times? What did you say, Brando? You woke up one last time?
Yeah, I think there were 22 times.
Let's see.
No, 23 maybe? I forget.
Thanks. It's been fun, so turn in your projects and yeah, come chat with me sometime.